this is a topic that has been touched on by past INE postdocs like Jill Baumgartner, as well as resident fellow Julian Marshall. So this is related to that work and the effort to solve this large global problem. In the United States, household energy needs are typically met with electricity and natural gas, or a combination thereof. But in developing countries, the picture is quite different. Solid fuels dominate, and solid fuels can be anything from coal and wood to animal dung, agricultural residue and waste, like what's shown in this picture, as well as a variety of biomass products that may be processed or unprocessed. And if we take all of the global population at 7 billion plus, represented here by this cluster of icons, the fraction in red represent the 41% on average that use solid fuel to meet their household energy needs. And that's equal to around 3 billion people. So a very large number. And there are a variety of impacts associated with solid fuel use. If we spread that around the globe, this is a figure depicting the percentage of population that use solid fuels by country. And so your eyes are probably drawn to the center. In sub-Saharan African countries, solid fuel use may exceed 75 and even 95%. So the dark orange is 75% or greater use solid fuels. The dark red, 95. Almost all people in those countries use solid fuels. In Asia, there are some countries where the solid fuel use is that high, but we also start to see the lighter shades of orange where solid fuel use may range between 25 and 75%. Notably, where my work is based in China, you'll notice that China is sort of a dull orange. 41 or 45% of the population in China use solid fuel, which is not as much as some other countries, but for a very large population, 45% is still a very large number. And 700 million households in China roughly use solid fuel to meet their household energy needs. So that's, you could use the equivalent of 2 United States worth of people that are using solid fuels. It's a very large number. And then you can see in North America and Europe, there's very little to almost no solid fuel use in South America and Central America, less than in Africa and Asia. So solid fuel use is associated with a variety of health impacts as well as environmental impacts. But it also has impacts on gender issues and well-being and livelihoods. And so I would be remiss if I didn't mention some recent findings from the UN Development Program estimate that women and girls spend around 20 hours per week collecting fuel wood, and that's time that could potentially be used for income-generating activities or education. And so the impacts of this issue spread beyond health and climate, though that will be the focus of the remainder of my talk. In someone's home, this is a home in one of the villages where our work has been based. Household air pollution might look like this from solid fuel, and you can imagine the equivalent of bringing your grill inside and cooking with it all of the time. The household air pollution that people are exposed to results in, or is linked to, an estimated 3.5 million deaths, mostly from respiratory and cardiovascular disease, on an annual basis. Another measure of impact of household air pollution exposure is lost years of healthy life. So if you're familiar with this, this is measured as disability-adjusted life years, if you've heard that term. It's a way of estimating the difference between the current health status of a population relative to the status of an ideal health population, or an ideal population where everyone lives to an advanced age free of disease and disability, sort of a utopian case. But that measure is really valuable because we can estimate the impact of various health risk factors based on the number of disability-adjusted life years that are associated with exposure to, in this case, household air pollution. And then we can rank those health risk factors against others and see which ones are most important. So when we do that with household air pollution, we find that it's the 4th leading health risk factor of all health risk factors in the most recent Global Burden of Disease report that was published actually just recently in the last couple of years. And that's 4th relative to high blood pressure, tobacco use, and alcohol use. So that makes household air pollution the leading environmental health risk factor, and it is more important on this ranking of global burden of disease than ambient air pollution, which ranks about 9th, and unimproved water and unimproved sanitation, which isn't even in the top 10. So what is it about household air pollution that's so bad? Combustion of any kind is incomplete, and so solid fuel burning in your home will produce CO2 and water, but it also produces products of incomplete combustion. And some of those are gas phase pollutants, and some are particle phase pollutants. And so that's what I'm showing here. As you burn, you get some particles in the air. And gas phase pollutants are, there are a wide variety of them. They haven't been studied quite as much in these settings. They're very hard to measure, for one. And also, they don't seem to make as big of an impact on health as particle phase pollution. So what I'll be focusing on is particulate matter, or PM, that's of a size less than 2.5 microns. And the reason we care about the size cut of the particulate matter is because over time, through the years, we've learned that particulate matter pollution, size matters, and the smaller the pollutant, the smaller the particulate matter, the more likely it is to have an impact on your health. So of late, we have been focusing on PM2.5 in this field. There's emerging evidence that even smaller particles, as smaller than 1 micron, which I'm showing here is black carbon, the aerodynamic diameter of that would be about 1 micron perhaps, that might be even more important than PM2.5. So the brief history is PM matters, PM10 matters, PM2.5 matters. Now people are like, I can measure stuff even smaller. PM1 matters, things less than a micrometer matter. And so the focus of our research is on PM2.5 and then black carbon, which I break out here to show it as a component of PM. So it's not like it's not necessarily a separate type of pollution. It might be in the core of particulate matter particles, or it might be on its own. But it is a component of air pollution that is emerging as important for health. We've already been interested in it for a while because it's viewed as an important pollutant to measure for climate, if you're familiar with it, as the second leading global warming potential after carbon dioxide. And these are very small pollutants, just for scale. This is as much of a human hair diameter as I could fit on the slide. So these are very small, and their size is important for their ability to get into your lungs and into your circulatory system. So call back to 1523, Paracelsus, father of toxicology. In more words than this, said the dose makes the poison. And I think you're familiar with this phrase. We have a source emission, in this case of PM2.5 or black carbon, that might or might not be well mixed within a home, and we could measure the household concentration. But that's not going to give us as good of an idea of a person's likelihood of a health response as knowing their personal concentration. So you imagine like Pigpen from Charles Schultz. That's actually, there's a lot of research in that area, and the effect around you, your personal cloud, your personal pollution cloud might matter more. So when we measure household concentrations, that's valuable information, but it's maybe even more important to measure exposure. So exposure is then the concentration measured in the personal zone times the amount of time you're exposed to that thing. So if you're outdoors for 15 minutes a day and you're indoors for the rest of your day, what you're exposed to indoors matters more than what you're exposed to outdoors. And then from the exposure, we then want to know what the dose is. So how much are you actually taking in? You can estimate that fairly simply by saying, I breathe 18 meters cubed of air per day, and I measured X micrograms per meter cubed of pollutant, so I know my dose. And the dose is really valuable from the health perspective because then we can plot the dose of the pollutant versus the response that we're interested in. And in the case of particulate matter, we're interested in cardiovascular responses and respiratory responses. So here, I'm going to walk through this slide. This is taken from the Global Burden of Disease report that I mentioned, and I want to use it to show how the distribution of health effects associated with particulate matter have changed over time. So in 1990, we're looking at household air pollution and ambient air pollution, and the bar represents the disability-adjusted life years that I mentioned earlier that are associated with that risk factor. And then the percent to the side is the percent of all disability-adjusted life years. So household air pollution in 1990 contributed 7% to all disability-adjusted life years. And ambient air pollution contributed about half that. The breakdown within those bars then is divided essentially among respiratory infections in the pink and red, lower and chronic respiratory infections, and then blue represents cardiovascular and circulatory diseases. And you can see that the fraction of respiratory has decreased as we move into 2010 looking again at household air pollution and ambient air pollution, the cardiovascular diseases and the circulatory diseases are making a larger contribution to the overall disability-adjusted life years. And this is an area of really groundbreaking and interesting research that Jill Baumgartner has presented on in the past, as well as others are now looking not just at the respiratory effects, but the cardiovascular impacts of exposure to, in this case, household air pollution. So I wanted to present some of that seminal work. Back in 1993, Dockery et al. Presented this finding, which I think you've seen presented before at either Frontiers or elsewhere, because this was a really groundbreaking result. We're looking at mean PM2.5 concentrations measured in 6 cities. This is known as the Harvard 6-city study, if you've heard of that, over several years in the 1980s. And then a cohort of 8,000 people were followed for, I think, about 15 years, and their mortality rates were measured. And so the ambient air pollution concentration shown here is, again, we're not in the home at this point. We're just measuring PM2.5 outdoors, is plotted on the horizontal axis, and the y, or the vertical axis, is the rate ratio, the excess mortality rate ratio. And so what you see, these letters represent different cities, the 6 cities that were studied, and the relationship is fairly linear. The higher the concentration, the higher the excess mortality rate. And this was a really groundbreaking finding at the time. These authors controlled for things like cigarette smoking and other dietary and health risk factors. So this was, among other studies at the time, was a really profound result. The other reason I wanted to use this is to show the scale on the fine particles. The horizontal axis here is 0 to 35 micrograms per meter cubed, because the next slide I want to show you is measurements taken in developing countries, household air pollution, where solid fuel use is going on. And that scale is now 0 to 10,000. You couldn't plot them together and make it meaningful. Now this exposure on the bottom is a concentration, but now we're looking at the personal cloud around somebody's head. And this work was published in around 2001, and it's looking at average daily PM10 exposure relative to 2 different respiratory diseases. So there's acute respiratory infections and acute lower respiratory infections. And what it's plotted against is the fraction of weeks with the illness. So this is one measure of effect, in this case a respiratory effect. And the shape of these curves, though it looks somewhat flat, it is logarithmic. It's an enormous scale, so it starts to flatten out. But the point here being that large reductions in PM2, or in this case PM10 concentrations, need to be achieved in order to achieve a health benefit, in this case reduced fraction of weeks with an illness. And so this was an important finding, and also just to give you a scale of different types of stoves that people cook with. That's what these black bars at the top, a 3-stone fire, so the traditional open, unvented fire in someone's home. Ceramic wood stoves, the range is a little narrower, and then charcoal stoves here on the far left is an even narrower range, but still in the hundreds of micrograms per meter cubed, so much higher than the concentrations measured in the Harvard 6-city study. Moving from the personal concentration and the exposure concentration to the dose, some of the more recent work that I mentioned that's making great strides in understanding cardiovascular disease impacts related to PM exposure looks at an estimated daily inhaled dose of PM2.5 on the horizontal axis. Here you'll notice it's on a log scale because findings for cardiovascular disease also demonstrate a logarithmic relationship between the dose or concentration and the cardiovascular health effects. On the vertical axis, the adjusted relative risk is plotted for a variety of cardiovascular effects that I'm not going to list right now, but the division of dots is the circles on the far right are cigarette smoking doses. So you're either light smoker, medium smoker, heavy smoker, and these are the relative risks that you'll experience based on those cigarette smoking levels, measured as an inhaled dose of PM2.5. And then over here on the lower left quadrant, are ambient air pollution as well as environmental tobacco smoke or secondhand smoke concentrations. And this here is the World Health Organization air quality guideline. So these are all above that guideline, and then you can see that for all of them, there's a relative risk that's higher than 1 for these cardiovascular effects or outputs. What you might notice also is a large gap in the data. And that gap is between about 1 and 15, maybe 12 milligrams of PM2.5. It so happens that that is also the concentration range in which you would find the doses in households where solid fuel use is going on. And so this is an area of research that needs more data. We don't have a lot of data on cardiovascular effects of household air pollution, and that's been referencing work from the former INE postdoc, Jill Baumgartner. She filled this gap. She was one of the first people to do this, and is a really profound result that the PM2.5 exposure, again measured in micrograms per meter cubed, and this is the personal cloud, is now from 0 to 600. So it's not as broad of a range as what you saw in the 2 slides previous. And she was looking at the impact on systolic blood pressure, which is plotted on the horizontal or the vertical axis. And you can see it's a logarithmic relationship, yet again demonstrating that we need large reductions in PM2.5 exposure to get even modest gains in health. And furthermore, these concentrations give you a daily inhaled dose of between 1 and 15 milligrams, which I think is just more evidence that this is an area of research that's needed. There's a gap in the data, and it would be really valuable to continue filling this. So the work that we're doing is building on this and looking at not just what is the baseline condition, but what happens when you intervene and change household energy with an intervention. What is the impact of that intervention on health? So instead of just saying, okay, we measure homes and they have maybe 300 micrograms per meter cubed of PM2.5 pollution, what happens if we shift that, reduce that pollution level by 100%? What is the gain that we might see? Based on this curve, we would hope to see if you're starting around 300 and you can get it down by an order of magnitude, will we see a significant gain in, a reduction in this case in systolic blood pressure? So household air pollution affects the environment too, and I don't want to leave this out because it's also a component of the work that we're doing, but it's less of a focus. So there have been a lot of researchers trying to understand the role of black carbon and its global warming potential. And a recent report called Bounding the Role of Black Carbon in the Environment, really seminal report, came up with this excellent figure, in my opinion, that I'd like to step through. So climate effects of black carbon emissions. This is the summary figure from their 250-page report. Warming cause, basically they state a claim that has been made in the literature, and then they have assessed, is this likely? Do we know the answer to this question? They're trying to identify challenges for this research. But for us, I just want to highlight warming caused by black carbon is concentrated in the northern hemisphere. These researchers say that's very likely. That the impact of black carbon on snow and ice can cause additional warming and contribute to snow and ice melting is very likely, but the magnitude of that impact is uncertain. BC in northern hemispheric latitudes can lead to early springtime melt, and this is considered likely, but the magnitude, again, is uncertain. I'm going to skip this one for right now. And then most importantly for our research, that absorbing aerosols may cause circulation changes over the Tibetan Plateau and darkening of snow, and the importance of this for glacier melting is currently considered unknown. Where that arrow is pointing is essentially where our work is located, which is why we're really excited to measure black carbon, not just for the health impacts part of our study, but also to gain a sense of what are the black carbon emissions from household air pollution, and are they contributing to black carbon regional emissions in different scenarios, and furthermore, is that having a real impact on climate? Therefore, if we know if it is, then we put in this intervention, can we see a decrease in that impact? And so it's exciting. When I saw this figure, I was like, wow, I don't even have to put an arrow on this figure to show you where I work. It's pointing to where we work. So I wanted to present this, although most of what I will continue talking about is more health-focused. So if we know that this is a problem, that household air pollution causes health effects and climate impacts, are we the first people to care about this? Definitely not. As Fred said when I walked in, this is a hot topic, at least within everyone's small field. It's a hot topic within my circle of colleagues. And in 2010, the Global Alliance for Clean Cookstoves was formed under the mission of creating a hub for NGOs, government agencies, researchers to come together, understand the state of the science, understand the state of the world, and develop solutions for addressing this problem of solid fuel and its attending health and climate impacts. And so they set this really ambitious goal of 100 million households having clean cooking solutions by 2020. That's coming up kind of fast. And this, I would say, has been largely a positive change in the field. There's been a lot of collaboration and people wanting to learn from each other, especially learning from programs that have already been in place. And so I didn't actually know this before I was preparing this presentation, but I did some background research on how many programs are out there, what are they doing, and I know that the general consensus has been that we've been failing at addressing this problem, and so I wanted to know a little bit more about that. Let's say there are around 100 cook stove programs that started maybe back in the 70s at the most. Some have discontinued, some have continued to present date. Some got started more recently, like in the last several years. They break out about like this. About 50% are non-governmental organizations. Another 30 or so % are development agencies, and then the remaining third is split between private companies and government programs. So it's kind of a diverse group of programs. And when looking at how these programs disseminate interventions to address household air pollution, most of them are looking at stoves, which is the focus of the Global Alliance. Some are also looking at fuel transitions, but stoves get the primary emphasis. And they disseminate these stoves in a variety of ways. Most use a market approach, around 70%, I think. So either full cost is fronted by the consumer or a subsidized cost. 25% currently involve carbon financing, 25% involve microcredit, and around the same 25% involve user feedback, which I think is sadly very low. It would be, I think, better, or, among the many ways that we could target change in these implementation programs, getting better feedback from users, I think, would be one of those ways. 100 million cook stoves is a lot of stoves. And as a comparison, and talking with Jill about this, who's my supervisor on this project, you could compare that to the number of Honda Accords that have been sold since 1976, around 12.5 million. The number of iPhones that have sold since 2008, a highly desirable product, around 250 million have been sold. And 100 million cook stoves is the goal, but how many households actually need new clean cooking solutions? It's 650 million. It's an enormous, enormous amount to be gained. And 100 million by 2020, no less, is an ambitious goal. I don't shy away from ambitious goals. I think that they need to be entered, though, with good information. And so the goal of our project has been to look at the impacts of an intervention and quantify the health benefits, quantify the impacts on climate or the reduced impact on climate because of an intervention, so that government agencies, NGOs, moving forward with a solution can do so with the knowledge that the intervention they're pursuing will have the benefits that they're hoping to see. So I also think that it's useful to say that among the cook stove programs that I highlighted, or that I looked up, the roughly 100, they were operating in these countries. These are the same countries, and you're looking here at thousands of stoves disseminated in those countries, and the cost per stove in those countries. And I wanted to show this to show that 100 million stoves is a lot, because 1 million stoves have been disseminated since around the 1970s. Granted, it hasn't had quite the same momentum as it does now, but I want to give this as a context for just how big of a goal this is. And then furthermore, the cost issue of how much it costs per stove has ranged from $1,400 to $1,400 US. And I think this is where we can learn a lot from the past, in that a place like Guatemala seems to be doing a pretty good job. They're spending a relatively low amount per stove, and they're achieving a wide range of dissemination. These numbers don't really take into account how long the stove is actually in use, so there is an issue that stoves might be disseminated and used initially, but they may fall into disuse, and that's not a trivial issue. It's just not one that I focused on in aggregating these numbers. What's missing from these two plots are two major players, which is India and China. And 100 million cook stoves is a lot, But it's been done. China's not on that graph because, again, the scale would be way off. In the 1980s, they disseminated new cookstoves in about between 120 and 180 million homes. So they already achieved this a couple decades ago. And those stoves are still in use. And those, in fact, are the stoves that, some of the stoves that we'll be replacing, because what they mainly did was contain the fire and provide a chimney. And that was a major gain, but it has not proven to be a large enough gain to see an attending influence on people's health and the emissions from a climate perspective. So I lead in with 100 million stoves is a lot. It's really hard to achieve, but it has been done, and I think moving forward it can be done, especially with the right information. So the key questions, I think, for evaluating these interventions that guide our research are, does the energy intervention reduce pollution and reduce exposure? And the next step beyond that is, does it also then improve or have a positive impact on cardiovascular health? And finally, does it have a positive impact on regional emissions, air quality, and climate? Those are the three key questions that are guiding our work to assess an intervention strategy that is going in place in the next year. And we hope to come out with information about what that can quantify the benefits on a health and climate basis. So our study sites are in several parts of rural China in order to capture several different types of fuel and cooking conditions, as well as something that I haven't mentioned thus far, which is heating. So cooking happens maybe several times a day, and it might happen for even several hours at a time. But that still sort of pales in comparison to how much you might be burning solid fuel to heat your home. So in the Sichuan site, heating doesn't happen as much as it does in the site in Inner Mongolia, where it's colder, and heating might happen for 24 hours a day for maybe even 6 to 8 months during the year. And they use coal for heating, so in addition, there are other health effects that are specific to coal that I haven't mentioned here, but we'll be looking at changing fuels and changing stoves to see if we can make an impact in these field sites where we're working. The pilot data from these two sites demonstrate that there is the potential for improvement. So looking at 24-hour concentrations and exposure to PM2.5 and black carbon, the black carbon fraction of the PM2.5 is shown in red. And these are for Inner Mongolia on the far left and the Sichuan site on the right. The two bars are distinguishing between individual, that sort of personal cloud concentration, and the kitchen or the household concentration. In Sichuan, it looks like the personal and household concentrations are more similar, and in Inner Mongolia, the personal concentrations are much higher than the kitchen concentrations, as well as being higher overall from the Sichuan field site. But I mainly show this to demonstrate that in both field sites, the World Health Organization mean PM2.5 guideline is exceeded by more than double in the case of Sichuan and many times over in Inner Mongolia. But also, we have the potential to reduce these pollutant concentrations, hopefully, with the intervention that we pursue. The intervention we're pursuing is a reduction in pollutant generation. So if we want to reduce the accumulation of pollutants in the indoor space, then we can do a couple of different things. So we can, but the one we're focusing on is reducing the generation of pollutants through low-polluting stoves, a transition to lower polluting fuels, coupling cooking and heating systems. I haven't dwelled on this very much, but because heating is a major issue that has really been ignored within this field, as you saw, it's the Global Alliance for Clean Cookstoves. Out of hand is not considering heating stoves, and within the field, people are starting to say, well, maybe that's something we should reevaluate. So we'll be looking at changing out a heating stove too in the future, and then some other passive energy saving methods. So we view it as an intervention package and not just changing out a stove in this case. But the stoves are the heart of, or the, sort of the spear of our intervention package. And these are some examples of stoves that I tested when I was working in China recently. These are these potentially ultra-low emitting gasifier cook stoves. And I wanted to just briefly explain how they might work so that you can see how they might be different. If you were to just burn an open fire, you would just have the fuel laid out and whatever air is naturally drafting through to feed that fire. In the case of these combustion chambers, the primary air is feeding the fuel at the bottom, but then that that gas is then met with a secondary stream of air that allows the flame to burn much hotter and allows it to drive to more complete combustion. Because as I mentioned earlier, products of incomplete combustion are really what we're trying to reduce. And it does appear that these stoves are doing better. They've been in development in the lab for several years now, the stove that we are looking at, so it's an iterative process, and I think that's something we really want to emphasize. It's not, stoves have to be designed for a variety, to meet a variety of needs, not just the technical efficiency needs. But we do start with laboratory emissions testing to look at the PM2.5 emissions that come from these stoves, and then we test them also in a rural lab that's meant to look more like a kitchen, so we can have it operating under those conditions. And the results from our data for the PM2.5 emissions from these stoves, these are a batch of the stoves that I tested in order to identify the performance that was the best among the stoves we were looking at. And so here, stove B had, in this case, 2 orders of magnitude lower PM2.5 emissions than that large bar on the far right, which is an open fire. And so, as I had been emphasizing earlier on, we need orders of magnitude reduction in PM2.5 concentrations, and so we start with orders of magnitude reductions in PM2.5 emissions. We're also going to be switching the community from crude biomass to biomass pellets, which have demonstrated also improvements in PM emissions. And this is an alternative that is now looking more attractive than it has in the past relative to coal, which was sort of the cheap next step up from crude biomass. So coal is running at about 100 RMB, the currency in China, per ton versus 600 RMB per ton for the biomass pellets. The biomass pellets represent a renewable stream of energy and potentially less pollution if they're used in tandem with these gasifier cook stoves. So that's sort of the twin key parts of our intervention are the new stove and new fuel. And in year 1, we aren't going to be introducing either one of these things. In year 1, it's a pre-intervention year, and we're going to be in 200 to 250 households in kitchens that look something like this, measuring air pollution in the household, measuring air pollution on the person in their personal cloud, and then also measuring emissions to capture especially the black carbon emissions. And we'll also be partnering or pairing this with cardiovascular measurements. So the first year is all to assess the baseline, and then in year 2, we'll be intervening in 50% of homes and installing the intervention, and then continuing to measure the same things, household air pollution and cardiovascular measurements for the next 2 years. Along with real-time measurements, we'll be collecting filter-based measurements, and I equate these to gold for our work because they are going to be an invaluable source of information about particulate matter pollution and its impacts on cardiovascular health to fill that gap of knowledge that I demonstrated is currently existing. And so longer term, we would like to use information from the filter-based measurements, which is capturing all of the particulate matter pollution in a course of a measurement, and then looking at the chemical analysis, looking at the impact that it has on different cardiovascular indicators of cardiovascular stress. And that's something that I think is unique or certainly on the cutting edge of the work that we're doing. This is what the intervention will look like, or a version thereof. The stove is actually within the traditional cooking structure, so that's what the cement block is. This is how most of the cooking that we have observed goes on in the places that we're working in China. There's usually 2 large open wok-like pans, and so the stove is actually inside. And I think one of the important things to note here is that this looks like cooking that people have already been doing, but we're changing out the stove, we're changing out the fuel, which is going to go over here and be, we've developed this device so that it can be easily fed into the stove. And I think these address major challenges to adoption. And I haven't talked a lot about adoption, but it's something I'm happy to talk about as I wrap up here. The primary questions that we want to answer once these interventions are in place is, can it improve health and by how much? And can it reduce climate impacts and by how much? So I hope that you've enjoyed learning a little bit about the work that brought me here to INE and that I'm getting off the ground. I leave in about a month to get the year 1 intervention measurements, or pre-intervention measurements started. And with that, I'd like to acknowledge Jill Baumgartner, who's been my supervisor on this project, and Sean Ming, who has been a close counterpart, and he's a postdoc at Tsinghua University, and also many other people at Tsinghua University who are collaborating with us to accomplish this work. So with that, I'll close and open for questions.